if you have isopropyl benzene mixed in nitric acid, sulfuric acid together, then there are several things that you need to consider. One, by mixing nitric acid, sulfuric acid together, that creates electrophile, right? Remember that nitric acid, sulfuric acid mixing together, you remove the water from the nitric acid, that produces nitronium ion. So we are talking about the nitration reaction of the benzene, but this benzene has already substituents, isopropyl groups. Isopropyl group is a alkyl chain. This is something that we consider activators, but not a really strong one because it's a sigma dominant. It puts the incoming substituents, nitro groups, either over the position or the para position because the sigma complex can be stabilized better at that position. So in the nitro groups go to para position here, then you're going to get this carbocation arranged by the resonance structures. But eventually the proton goes away, you go to nitro at the para positions. You can also get at the ortho position, the proton goes away, and you get the ortho nitro, and also nitro goes to ortho positions. But it's not making this. That is not going to be formed. It forms either ortho or the para positions. So when the benzene already have a substituent, then you have to think about where the incoming electrophile is going to go. These are bromine with a ferric bromide. If you're just using a bromine alone, no reactions, nothing's going to happen. But with the ferric bromide, bromine together, what happens is it creates brominium ion, supposedly. It's not exactly brominium ion, but equivalent to brominium ion. That brominium ion is going to be the electrophile attacked by the benzene. But it has a substituent there, which is electron join groups. Carbonyl is electron deficient. So it pulls the density out of benzene. So it slows down the reaction, and that makes it meta-electrons. So let the benzene, bromine, I'm sorry, go to meta position here. Make the carbocation as a para position. It can go to ortho position by making resonance structures. It can move to another ortho position by making resonance structures. But you can clearly see that the cations always miss the position that bears the electron between groups. So that's the why the meta position is the best. And then the proton is going to be taken away. Then you get the products formed, the bromine sitting on the meta position. That's the one you're going to get. Not all the para substitute. I really like this question because it looks very, very simple. But this should remind you that you cannot simply memorize the thing. And then we always ask this question, and not always, but most likely ask this question in the test, in the quiz as well. All right, let me show you how things would go. Well, kind of a similar situation. We got the substituted benzene, amino benzene, and then we have reagents, nitric acid, sulfuric acid mixed in together. So nitric acid, sulfuric acid mixing together, what it creates nitronium ion, right? That's electrophile that gets attacked by the benzene. Benzene attack these nitro groups, but we already have a substitute there, amino groups, which is activator, right? Not only just activator, these are pyruvate, these are really strong activators. And then those activators has a preference for the electrophile, which is always the para position, right? So what we probably would think is we recognize benzene as a electron groups, which is all the para directors. We identify what is electrophile. So you just move on saying that, okay, electrophile going to para position or the ortho position is going to create this intermediate. Proton's going to be lost, and then going to be stabilized by the resonance structures. I've just skipped over the rest of that extra stabilizing resonance structures. But in the end, the proton is going to be lost, and you get to produce the product, either the para position has nitro groups there, and this is basically what we can expect for as an answer for this question. Right? That is basically what you would answer. And then, and somebody saying that, okay, paras are not the only one. Order can be also shown here because we got order para. So both will happen. And then I'm going to cross it out. Probably you already like me because I can do this thing. The question is, there's nothing wrong there. All the logic that I told you is what we talked about, right? These two make the intermediate under the electrophile, and then this is substituting benzene, which have a strong activators. So it's got to go to the para or to the para position. That's what we have talked about. So why I consider that was wrong? Yeah. Have you ever taken this course before? Normally, I get no right answer, but yeah, you're right. This is where you could be fooled. This is electron withdrawing groups. I mentioned this is electron withdrawing groups because it has a lone pair. But oxygen lone pairs are not basic, but nitrogen lone pair is a basic. What this basic nitrogen lone pair does in this strong acidic condition, this is the acid, this is the base. So what happened? They get protonated. When amine becomes protonated, it becomes an ammonium group. That makes a nitrogen permanently positively charged. And I told you, permanently positive ammonium group becomes a very, very strong electron withdrawing groups. So this looks like electron donating groups. It's going to be electron donating groups, not this condition. But acidic conditions make this one protonated. Now it suddenly changes to electron withdrawing groups. Now we have to think about this electron withdrawing group sitting on the benzene, even though I draw amino groups there in the question. But with an acid, it's going to be protonated, becomes electron withdrawing groups. And the electron withdrawing groups, you know that, is a meta director. So it puts the nitro, the meta positions, avoiding all the para positions. They can make the resonance structures, avoiding these positions, but in the end, you get the nitro going in the meta position. That's the product. This proton, will we get rid of it at the end of the reactions? So this is a product. So this is a very tricky, I know that, but this is a trick that we play a lot. This asks you to whether you understand the nature of the substituents under the given conditions.